Okay. We have fewer announcements today. There's still a programming assignment that's out and it's due September 27th. But please take a look at it now. And the lecture videos are on YouTube, and that's a good thing. But it's also good to come to class. So anyway, you make your choice. Today we're going to be talking about a little bit about memory model, a little bit about memory allocation, and about linked lists, and maybe actually we'll never get it to list abstract data type today, but we'll try. Does anybody have any questions? Okay. So we last time talked about memory as being this giant array, and the addresses that are used by the CPU to store information into that giant array are called pointers in C. So pointers are like variables, but they contain a value which is an address. It's like a zip code or whatever for a particular data element that's stored in memory. So I have three questions on this slide. Well, there's four, but in the top part there's sort of three questions. One of which is a kind of syntax question. What type is Q? So we know that P, for example, is a int star. What is an int star? It's a pointer to an int. So it's an address, it's a memory address, and in addition, the compiler now knows that that memory address will contain an int. Okay, then there's some other stuff, and then there's this part right here, which is output. And so there's two questions about what values are being output by these cout statements. And let me just ask, how many people are comfortable right now answering these questions? How many people are really uncomfortable answering these questions? Somewhat uncomfortable. Okay. So what I thought we could do is just you all figure out what the answers to these questions are, and then in 1 minute or 2 minutes, I'll ask you, and we'll see how it goes. Okay? Maybe 1 minute, maybe 30 seconds. But go ahead and talk amongst yourselves and try to figure out what the three things are. What type is Q? What is output by these two cout statements? And if you have questions about doing this, raise your hand and I will come and visit you. I might visit you anyway. So three questions. Anybody ready to answer the first question? Or maybe you're still working. Sorry. Okay, now I can't wait any longer. I'm too excited. What is the answer to the first question? What is the type of Q? We know the type of P, it's a pointer to an integer. What is the type of Q? Yes. Integer. Whoops, hold on just a sec. Okay, hold on just a sec. Okay, hold on even more. There we go. Okay. I would really like to write down integer for you.
Technical difficulties. Stand by.
But please stand by. And in fact, maybe what we'll do is we will save this and we will kill this and we will open it up again. Well, this is going to be fun. Because it's infallible. It's totally infallible. Let's see if this erases. Yeah, it does. I just can't write anymore. All right. Well, this is going to be an interesting class if I can't write. I know what I can do. If I can't write, I can use the previous lecture's slides with all the writing already on them. It's brilliant, but we won't want to do that. We want to do this.
Try number 30.
Well, this is strange. All right. I'll tell you what they are. What type is Q? It's an integer. Why is it an integer? Why isn't it a pointer? Because C is got strange syntax. So when I declare Q to be a variable in the same line as P, the problem is that the star is associated with the variable name. It's not associated with the type. So you might say int star P and Q. Therefore, Q is also an int star. No, the star goes with the P. And so if there's no star in front of the Q, then Q is simply an int. I know, it's strange and annoying. Just like this cross, strange and annoying. Now it's really strange and annoying.
You try switching to a different tool and then switching back to that tool.
I'm going to try that. Oh, I could try writing with the eraser. Does anybody have another one of these pens for a surface? Because I could try another pen. Can I try your pen?
Did you try it? Did you select the red pen? Switch pens, like you just...
I tried, that's exactly what I was on. I was on the red pen. So now I've selected the, now I'm back to selecting the red pen. And so now, nothing. So my guess is that my pen is running out of juice. But
then you can swipe with it, right? So that means the input from the pen is still.
Can I write with my finger?
No. Does the pen like still register inputs on the screen? If it does, that means that it's not the pen, because then it's still registered.
The back does, but not the front.
So the front doesn't work anymore.
Correct.
Well, that's strange. Have you tried taking the battery out?
But nobody has another one of these.
Oh. I do.
You do? Do you have it with you? Can I borrow it for just a second? This will be an experiment. Unless it works.
Wait, can I borrow your pen? The other one that doesn't work?
Let's see. What could possibly go wrong?
It's a newer model, I think.
Can I borrow it? Oh, thank you so much.
Wait, can I take a look at the...
No, you may not. Because now it's working. But you can take a look at this.
Yeah,
this is useless.
Because I want to take out the battery and put it back in, because sometimes these bug out.
Okay.
I've had one of these for a long time, but they kept going out.
So what type of... It's an int. Look at that. I'm excited. All right. Now what happens? Yes?
I have one question. In C, is it generally a bad thing to leave integers and pointers uninitialized? Like, how it...
You mean when you declare them, you should initialize them?
Yeah. Like, is it better practice to leave them uninitialized or to, like, set them to 0?
Is it better practice to leave pointers uninitialized when you declare them or to initialize them when they're declared? There is no better practice involved in that, because it may be that you don't want to declare that pointer until later on when you get into a loop, but you have to declare it outside of the loop because you want to use it after the loop. Then you can't, I mean, you could, if you'd like to, declare it to be null when it's declared, but that's just craziness. I would just declare it as being a, I mean, it's perfectly fine just to declare it like that. The real lesson from this is don't declare multiple things on one line unless you really know what you're doing. Because why wouldn't you just say int star p, and if you meant q to be a pointer, say on the next line int star q. It's perfectly fine. Yeah.
You can't declare two references on the same.
You can, but you have to do this.
Yeah.
You can do that, but I'm suggesting that you don't. Because it's so easy to forget that little star, and then, you know, it's just terrible. Yep.
Try it. See if it works now.
I don't know. I like this one.
It might work now, though. It hasn't worked on mine.
Oh, that's interesting.
You twist it, you twist the back, take out the battery, put it back in, and then it should fix most issues.
Now, you'll learn something new every day. So hopefully we'll learn more than that. But anyway, that's a good thing to know. And I do not want to walk away or leave this anywhere. So now tell me about the rest of this code. So what happens next, we declare an integer variable. When we declare an integer variable, this variable is declared as a local variable on the current call stack. So it's a local to this procedure. That is, if the procedure that I haven't written what the procedure is, if I called that procedure again recursively, it would, for example, get a new call stack that would sit on top of that call stack. And so I get this one part of memory which is called the stack memory. And things that are declared like this are declared in those local activation records on the call stack. So they're call stack. Which means that when this code finishes this integer x, its memory vanishes. But right now, when we've declared x, there's a little box, and its name is x. So whatever's inside that box contains x. Whatever's in it is x. Right now it's not initialized, so it's just sitting there saying int. Then the next line, p equals ampersand x. Ampersand is a function that gets the address of. So ampersand x would get the address of this box, and it would, for example, if this box, which is the location where x is stored, if that location was at 0x0007, then p would be equal to this. So p is an address. It's an address of an integer, and currently there doesn't seem to be any value on x. But if we do star p equals 6, star is the dereferencing operator for a pointer. So if I put star in front of p, that thing, if p is a pointer to an integer, is an integer. And the interesting thing about star p is that it not only gives you the integer, but you can actually assign to it. So it's not only a right value, it's a left value. Here, star p is acting as a left value, meaning it's on the left side of the equal sign, and it can be assigned to. But it also will be a right value if we put it on the right side, and it would give you the value that's within that box. Currently, there's no value in the box, so we don't get anything. But this thing says, whatever the address for that box p, dereference it and assign that 6. So it stuffs into the memory location 0x007 or whatever p is, it stuffs in the value 6. So now, what is the output of these two lines? The first line will just output 6. The second line will output what? 6?
Whatever address you wrote.
The address.
The address. 0x0 blah 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 7. Okay, so that's the answer to the first 3 questions. And now class is almost over. No. Okay, write a statement that outputs the value of x using the variable p. Quick! How would you do this? I just told you how to do it. You have to use the variable p on the right-hand side. It's a right-hand value as well as a left-hand value. So you can access the value that's pointed to by p by using the dereference operator star, cout star p. That will give you the value of the variable x. So you now have 2 ways of accessing that value. You can use x or you can use star p. Okay? Okay, good. Now, if I was, I've been lazy. Actually, the reason that I did this was because I don't have room to put more than one line, more lines on. So I have 2 pointers, both of them pointers to integers. One is called p and one is called q, and this is something new. This new call is a call to the memory manager for the entire program. And it looks for memory not on the stack memory that's local to a procedure, but in global memory that's over on the heap. This is heap memory. So this allocates heap memory for an int. Oops, that's not an it, it's an int. For an int, and returns its address. This is not allocated on this in the same memory block as the local variables in a program, because the local variables, when the function exits, those local variables go away, and that memory that was used by that execution of the program goes away as well. These things, the memory that's allocated by new, the stuff that's allocated off the heap memory, that is permanent. It doesn't go away until the entire program terminates, like it stops running. Why in the world would you want that? Why are there these 2 different types of memory, stack and heap? It's a puzzle. Yes?
Say because the stack, like, it's a more limited resource, but it's really fast, so it's good for small data types, but heap is better for when you have really complicated data structures that are super long. There's stuff over there.
Well, they may or may not be faster. I mean, I don't really know. But the point is it's a very good point that the stuff that's allocated locally on the stack is local, and it's going away. So if I had a function, for example, that wanted to set up some data structure and allocate some memory to create something, that creation, if I only used local variables, would go away when the function exits. If I wanted to create it for use by another function, I have to use something like new, or I have to pass things around. But even then, I'd use new for that case. So heap memory is more permanent memory, more permanent than local allocation. But local allocation doesn't need to use the memory manager. The memory manager is the thing that decides what memory to give to you when you call new. It looks for free memory and says, here you go. Here's a piece of memory that's the size that you want, and you can use it. Okay, so we use it. Well, the first thing we do is so now we've created this piece of memory, and P is given the address of that memory. Now, probably it's something different than what would be allocated on on the stack, so let's give it a different, and it's something like A. This is 0x means a hexadecimal number, so that's all these addresses are printed out in hexadecimal notation. So P is equal to this. And another way that we have to write this is when you have a pointer to some piece of memory, we use notation that looks like this. P points to that memory. So when I perform this Q equals P, I'm assigning Q to be exactly the same value as P, which is 0x00 through to A. And it makes another pointer that points to the same location as P. It has the same address. P and Q contain the same address, and that address points to that box. Is this true? Is that a true statement? It says the address of P is equal to the address of Q. No, those are two different variables. They've been allocated locally in this function. They have an address which is over here on the stack, and they're two different variables. They have two different addresses. So their addresses are not the same. So no, not the same. But they do point, they have the same value, so they both point to the same location. So, but they have to be stored. Every variable has to be stored some place, and P and Q are variables that are stored in their own separate places. And this ampersand operation, it calculates the address of those places. Yep.
So the ampersand of pointer is the address of the memory where, like, the pointer exists.
That's right.
Not the address that the pointer.
Correct. And in fact, ampersand anything is getting you the address of that anything. Now, please don't be confused by the fact that ampersand is also used to indicate a reference parameter. That's another use of ampersand. You've seen that before. When you pass in something to a function and you want the function to change it, you pass a reference to that thing into the function, and then any changes that function makes are reflected in the caller's scope. So that's another use of ampersand. It's sort of related, but it's not. It's not the same thing. Okay, so now I set star Q. That means star Q is dereferencing the pointer Q. It's putting it on as a left-hand value. It's assigning 8 to it. So we know what that does. It stuffs an 8 in this box. And then we see out star P. What gets output? 8. It's the same memory location. P and Q are both pointing to that same memory location. We used star P to set the value to 8. We're using star Q to get, or no, we used star Q to set the value, and we're printing out star P. It's just getting that value from that box. So this would output 8. Now what we do is we say Q is equal to a new 8. So we're creating a new integer. We are no longer having Q point to that box. Q now points to this box. And we're setting star Q to be 9, so we're filling up this box with a 9. And then we're setting P to be null. Do you like this? I don't like it, but why don't you like it? I don't like it. Well, I should ask you. Do you like it? And why not? Yes. Yeah, what's happening here is when we set P to be null, we've lost our only access to this memory location that we've allocated out of the heap. So when we essentially erase P by setting it to null, we've lost the ability to access some allocated memory that we've allocated using the heap. And so when that happens, this is a memory leak. The program can no longer access some allocated heap memory. Why is that bad? I mean, you don't like it, but why is it bad? Why are leaks bad? Who cares if I can't allocate that memory? Yeah?
Wastage of memory. Memory is a scarce resource.
Memory is a scarce resource, and we can't use that memory again. Yeah, and in fact, memory is, when you think about it, it's not that scarce. Memory is huge. But then again, you keep writing programs that have these giant for loops in them that could potentially allocate lots and lots and lots and lots of memory. And if they never deallocated that memory, if they never told the memory manager that this memory is no longer needed, and they just lost track of it, your program just lost track of that memory, pretty soon there would be no more memory for you to use. So memory leaks are bad because they waste memory that could be used for other things and could potentially lead to, if the program runs for long enough, the program running out of memory. So that's why it's bad. And so what you do instead is, before you set the pointer to null, you delete the memory that's pointed to. So what I really should have done here, I really should have added this line, delete P. That will make this okay. But without this line here, I'm going to lose track of that memory that was allocated. So this is good. This part here, I delete Q, and then I set Q to null. That's okay. So we like this. Not only is it okay, but it's actually preventing, by setting Q to null, we're preventing another problem that can occur, which is that if you don't set Q to null, Q is still a pointer. It's still a valid pointer to some memory location. You still can access memory via the variable Q. It's just no longer guaranteed that that memory is going to be what you expect, because the memory allocator has been told that you don't need the memory that's pointed to by Q. It's been told that it could delete Q. So it does. And now it's got lots of things to do. There are people that are asking it for memory all the time. And so in between the time that you delete it and the time you look at Q again, you do a star Q, in between that time, it could very well have replaced whatever's in this box by something strange, like the beginning of the word elephant. That could now be the letter E, for all you know. So this is what is called a dangling pointer, but it's a reference to an unallocated memory. It's not allocated anymore, but you have a pointer to it. And that's not good. Okay, yeah?
Does it matter when we delete it first, or if we set it to null first?
Oh, if you set it to null, what will happen? If you set it to null first and then you say delete Q, what do you think will happen?
To return the memory without itself.
What information is actually being passed by the call delete Q?
To return the memory back
to the memory manager.
Okay.
But it only knows about that memory because you've passed in the value Q. And if you call delete Q after you've set it to null, then what you're passing into the memory manager is delete a null pointer, which is okay. You can do that, but it doesn't do anything. It needs to know what address you're trying to delete because it has to know what memory you're actually wanting to free. So that value, that pointer value of Q, has to be a valid pointer in order for it to do anything reasonable. Now, it just turns out that if it was a null pointer that you passed in, that case is handled by treating this as a no-op. So it recognizes that you passed in a null pointer and it won't do anything. It won't, for example, segmentation fault or anything like that. But it won't do what you want, which is to delete the memory that's used to be pointed to by Q.
So would you say if we set it to null, then we technically do reference it already?
Well, you've lost it. Once you've set it to null without deleting it, it's gone. Unless you have another way to get there. Unless you have another pointer to it. Yep. It's the same as it was before. The delete operation doesn't change Q. I suppose it could, but that would be confusing a lot of people. But what delete Q does is it just tells the memory manager, go to location Q in your table of what you've allocated and mark that as now being okay to use again. The memory manager it's an amazing algorithm because it has to be able to allocate arbitrary sized blocks of memory. You might, for example, ask not for just an integer, you might ask for, I don't know, like a genome structure, which is, 10 to the 9th base pairs long. So this huge chunk of memory that it has to allocate for you. And it does that, and it tries to allocate consecutive memory. In fact, it does allocate consecutive memory blocks. So it gives you a consecutive chunk of memory of whatever size you asked for. And think about that. Okay, I allocate these blocks, and then all of a sudden I start deleting every other one. Now I've got, instead of a big chunk of memory, I've got a little bit used here, then a space, then a little bit used here, then another space, then a little bit used here. Now what do I do if they come in and they say, I want this much memory? I have that much memory, but it's fragmented. It's all over the place. What does it do? Interesting. It's a great algorithm. It arranges, who knows what it does. Yes?
After deleting the pointer, is it needed to make it null or it's optional?
No, you must make it null. No. It's optional. Totally optional. But you will get into trouble if you ever use that pointer again. Like if you try to dereference it, you might not get what you expected. Like for example, if I didn't set Q to null, and right here I wrote cout star Q, you would expect, and I would expect, that you would get back 9. But there's no guarantee that that's true, because you've deleted that memory. It could have been reused in between the time you deleted it and the time cout occurs. In fact, the memory manager might have said, oh, that's exactly the size memory that I need to do the following thing. I'll just move some stuff into it, and there we go. And then you ask star Q, and it's no longer 9.
So deleting a null pointer, is the no operation only guaranteed for primitive types, or if you did it on like your own data type, would you have to do something in your constructor?
A null pointer is just a pointer, and so it's just an arbitrary to anything. It will say fine, done, even if it's a pointer to a human genome. If it's a null pointer to a human genome, it's still a no-op. Okay. Dereferencing a null pointer, however, is not good. So, for example, if this was still here, and instead of couting it, if I did this, so let's look at this. This right here, Q is null, so I'm dereferencing a null pointer. When I dereference a null pointer, what do you think happens? I'm trying to get a value that's at memory location 0. What happens? Segmentation fault. Your program crashes unless you've written it to catch segmentation faults. But that's probably not what you intended. A segmentation fault occurs when you dereference a pointer that's not within your segment of memory. You have an allocated range of addresses that you can use. 0 is never in that range. So whenever you dereference 0, it's a seg fault. Also, if you guess small numbers like 1 and 2, those are usually not in your range either. So small arithmetic on pointers is also prone to creating segmentation faults. Okay? All right. This is the first structure that we've talked about in class that's not an array. This is a node in a linked list. Let's take a look at it. First of all, it has this weird template line with a thing called lit. What is a lit? Well, this is a variable type. So this means that I could create a node whose where lit was set to be an integer. Or I could create a node, so let me write down variable for type. I could create a node that contains an integer. I could create a node that contains a string. I could create a node that contains a more complicated data structure. And all of those would use this same code template as the definition of node. The only thing that's different is what is the type that's stored in the data field. So that's a templated class or a templated structure. This thing here is a structure, but a structure is just a class. It's the same thing. The only difference between, well, there's probably some technical difference that I don't understand, but the only real difference as far as I know is that structures are, the fields within structures are by default public, and the fields within classes are by default private, and so that's pretty much it. So this is a structure or a class called node. It has some data in it. The data is one of the fields in the structure. And the other field, so this is the data field, and that data field could be an integer, it could be a string, it could be a whatever. The other field is, it's a reference to a node. It's a node pointer. So this other thing, next, is a pointer to another node. It could be null, but it could be a pointer. And if it's a pointer, it's pointing to another one of these things, which itself is a node with data and a next field. And that next field could point to something else. And that's why it's a linked list. It's nodes that are all linked together by this next field. As I walk down the list from next to next to next to next, I go to different nodes in this chain. It's a linked list. This is how Racket does all its lists. They're linked like this. Which is also why there's car and cdr. Did you learn about car and cdr in Racket? No? I am so disappointed. Racket is a variant on Lisp. And in Lisp, the access to lists involves taking the head of the list, that is taking this guy, or taking what remains, the remainder of the list. Car and cdr. In any case, you don't need to know that for this class. Sadly, you don't need to know that for the Racket class, but that's okay. There's one other thing in this declaration, the struct declaration, and that is a constructor. This constructor takes in data, a thing that will be set to the data, and a thing which is an X pointer, or by default, it's null. So this little equals is specifying this parameter as having a default of null. And what it does is it uses a list of initializers to initialize the data to be D and the next field to be P, this pointer that's been passed in. And so it's constructing a new node. So if we wanted to construct this node right here, we could say, for example, we're going to create a node of type integer, that's the data type, that's filling in this lit value with int, and we're going to declare head to be a new version of one of these nodes, which has as its data value 8. And so to create that, we just need this one line. Declares head and allocates a new node with the value 8. How do we do this? This guy. You can do the next guy in one line, so maybe you should think about this. Is this a good thing to think about, or should I just tell you? How do you feel? It's the afternoon.
It's okay, there's only 10 minutes left.
No. 10 minutes is plenty of time to answer a one-line question. Do you want to do it, or you want to just know? How many people want to just know? It's okay. How many people want to actually think about it?
Sure.
Okay, think about it for 2 minutes. Go. Talk, discuss, think.
Got it?
Pardon me? Node is class, and I'm defining the class here. LIT is a data type that is used to construct the node. Well, LIT could be an integer, or LIT could be a string, or it could be something else that you define. It's just, this is saying this is going to create a linked list of nodes, and the data in each of those nodes is of type whatever you tell me, lit. Whatever lit is, that's the type of data that's in those nodes. This is really the definition of one of those nodes in this sequence. For the last line, the constructor, it takes in two parameters, or one, because it has a default value. And then after that's colon, there's what's called an initializer list. And the initializer list is that syntax where each field of the structure, parentheses, whatever you in there, and then you do the whole thing. And then there's a body to this constructor, but the body is empty. So curly brackets, it's empty, that's an empty body to the constructor. Oh, you could put in like, I don't know, see out, I've been constructed. Anything you'd like, it's a function. So it's just called
why would you
initializer list? Yeah, why didn't I just put it in the function? Because in some ways, sometimes it's more efficient to do this. It doesn't call an extra constructor sometimes in certain situations.
Okay, so when we call it, there's some stuff to do after.
The colon means there's an initializer list.
So when you're doing stuff like this, it's more for classes.
Yes, it's exactly the truck is a class.
So for doing this, or
me, I don't care. I mean, I can do either one. But if you're like in C++ production mode, and you want to consider doing this if you're seeing slowdowns due to extraneous constructor calls.
How does this skip constructors in cases?
That's complicated. I'd have to draw you a picture. I don't even think that I can draw the right picture. No, I mean, if you really want to know, and you probably really do want to know, I'd look it up. You can just, when should I use an initializer? And Stack Overflow, all kinds of examples, which is how I learned about this. Okay, everybody ready? Here we go. What do I write down? Anybody want to volunteer? We can't have everybody speaking at once. I know we like all talking at once, but no. One at a time. Somebody? Nobody? Oh, you've answered. You haven't answered today.
So at equals new node in, and we pass in 6 at.
Excellent. It's taking the old value of head, it's putting it together with 6, it's creating a new node by calling the constructor. That new node is allocated by the memory allocator. It's given an address, and that address is returned as the new value of head. Any questions about this? Yeah.
General question: what's the point of all this pointer stuff? Like, how is it helpful?
What is the point of the pointers?
Yeah. How does it? No. What's the benefit, programming-wise, from having all the pointers? The ability to do this.
Over not having pointers?
Over it being automatic with Java or something like that.
Oh, because you can do a lot of low-level stuff that you can't do. You can do pointer arithmetic on these things that you can't do in those higher-level languages. Whether you want to or not, I don't know. But that's one of the features. Another feature is that you don't have a garbage collector to collect up garbage that you've lost. So in Java, you have a garbage collector, which sometimes kicks in when your Apollo lunar lander is coming down onto the moon and it kicks in and starts garbage collecting in the last 30 seconds. That's not good. So this will never garbage collect on you. But then again, it won't free memory for you for free. So there's a lot more. It's sort of like C is a more low-level language, and C++ inherits that.
So the garbage collector can sometimes do what you don't want it to do.
It takes time. It's collecting garbage at the wrong time.
Ah, okay.
Yep. So if I, instead of writing this, if I, instead of writing new here, I wrote star. Before head, write star. Here? And don't write new? Okay, let's see what this is. What's a star head? A star head is a node. And this is a node. And sure, it would work. If you have a copy constructor, it will copy this node into this node. So it would obliterate this. And it would copy in this thing. So it would replace head by this, and there would be nothing that head would be pointing to. Well, it would point to some, but it's like, no, it wouldn't be circular. It would be pointing to, yeah, what would it be pointing to? Maybe it would be circular. That would be cool.
Is that bad?
No, circular linked lists are awesome. Let me just tell you, they're the best things ever. You think that I'm being stupid, but I am not. That's exactly what your first programming assignment is about. And not only singly linked, this is a singly linked. It's linked 1, 1, 1, 1, 1. One link forward, no way to go backwards. Yours are doubly linked. And they're not only doubly linked, they're doubly linked and they're circular. And they're not only doubly linked and circular in one way, they're doubly linked and circular in two ways. Going this way and also this way.
Wait, how does doubly link work? We'll have 2 pointers to...
Correct. Next and previous.
Ah.
Yep.
So, I missed what did you figure out what happens to that? Does it wipe the data first and then make it point to nothing, or?
Well, this is going to create a node locally. It's going to be a local node thing. Not a pointer to a node, but a node structure. And then this copy, if I didn't have the new here, this is going to copy that structure into the structure that's pointed to by head. So the current structure pointed to by head is this guy. And so it gets that new structure copied into it, obliterating what's there. Now, the point is that this would actually copy the address of this thing into here, so that what you would get is something that looks like this. 6. So that's what this would do. Okay, but please remember that this is, I should have done this in different color. Here, let me erase it. This is what the regular way to do things is. And this new way of doing things, which we will try to do in blue, this will never work. This, if I kill this, and I put a star here, this would produce that. I think. Probably.
So the difference is it doesn't evaluate what's on the right side first?
Well, there's one difference, which it doesn't allocate any new memory. It's only creating a local object, which is one of these node things. That's what's one thing. Second thing is that it's doing a copy of that object. So it has to know how to copy objects, which it knows how to do. So there's a object copy that's going on here. That's the part that I'm less certain about, because it may be that it doesn't know how to copy these objects, in which case it will complain. You don't have a copy constructor for it. But let's just assume you did have a copy constructor for it, something that would tell it what to do when it has an assignment from one object to another. Then it would do this. Okay, I will see you on Wednesday.